Okay, so in this chapter we will be discussing some functional groups, some organic compounds containing functional groups. These compounds are called as alcohols, phenols, thiols and ethers. We'll look what these compounds are, what are the functional groups that they contain, how do we name them, and what are different types of reactions that they undergo. Okay, so let's first begin with what exactly are these groups. So these alcohol, phenol, thiol and ethers, they consist of functional groups. There are a bunch of other functional groups that we will study later on in this course, but basically this is what we are going to begin with. Functional group is when you have a hydrocarbon and it has a specific group attached to it, where all that group basically provides that compound with certain physical and chemical properties. Okay, for instance, an alcohol consists of a hydroxyl group, and because of this hydroxyl group, all the alcohols have very similar properties. Therefore, they are called as one functional group because they impart very similar properties to the compounds that consist of this group. Okay, so first functional group is an alcohol. It always consists of a hydroxy. So as long as there is a hydroxy group on a organic compound, that means it is an example of alcohol. The next group is phenol. Phenol, we already saw what was phenol. Phenol is when we have a benzene ring and it has a hydroxy group attached to it, it is called phenol. Okay. Next is thiol. Thiol consists of an SH group. So if we have an organic compound that consists of a group SH on one of the carbons, that is called a thiol. And lastly, we have ethers. Ether consists of a COC group, meaning between two carbon atoms there is going to be one oxygen. Those are called ethers. Okay, so a COC group, sometimes you might also see it written as an ROR group. Ether. Okay, what is R? Usually when we talk about organic chemistry, it consists of bunch of hydrocarbons, right? So let's say it consists of this hydrocarbon and then I have an OH group right here. Okay, this zigzag line means I have a bunch of carbon, hydrogen atoms, right? So this sometimes is referred to as R. Generally, I would say this whole thing is an R group. So instead of writing all the time carbon, we simply say, okay, generally this is an R group. So simply when I say thiol would consist of R with an SH. R here basically means this is an alkyl group. It consists of bunch of carbons and hydrogens. This is an alkyl group. Similarly, if it is an ether will consist of ROR, means there is an oxygen and there are carbons on both the sides of this oxygens, carbon and hydrogen. You could draw it better like this. But basically there are certain number of carbon, hydrogen on both the sides of that oxygen. That would make it ether. Okay. So now let's look at each of these groups separately. First thing, we'll start with alcohols. Alcohols consist of OH group. How do you name alcohol? If it is a normal simple alcohol, like you see this molecule, you have one carbon, it consists of an OH group. Okay. So how do you usually name them? You name the alkane first and then replace this E with OL. So what would the name become? The name would become alkanol. That is how the alcohols are named. You replace the end E with OL. So for instance, if this is the group, what is this? This is the compound. What does this consist of? It has one carbon and one hydroxy group. When I see hydroxy, I know this is alcohol. Okay, and what is the rule for the alcohol? You name the alkane first. If I were to name this alkane, it would be one carbon alkane, meaning methane. So now I replace this E with OL, it would become methanol. Okay, And where is the alcohol located? Alcohol is located on carbon number 1. It is 1 carbon, so I really don't have to tell exactly where the alcohol OH group is located. Therefore, it is methanol. Then you see this compound right here. How do we name it? First thing, you have to identify what type of compound is it. Does it have a functional group? It has a hydroxy group, which means this is an example of alcohol. Again, how do we name alcohol? You name the alkane first. So what is the alkane here? This is ethane, 2 carbons. So this is ethane. Now I simply replace this E with OL. So it becomes ethanol. And if I were to tell where exactly is the hydroxy group located, I would name it like this: 1, 2. Because again, you would give preference to the substituent that is added. So this would be carbon number 1. So actually it is 1-ethanol. But remember, if it is 1, you simply don't write it because it's known that this is on carbon number 1. So this would be called ethanol. But if this hydroxy group is located some other place, then we would have to tell the number where the hydroxy is located. Okay. For instance, if a compound is like this, how would we name this compound? The naming of the compound is very similar. Okay, you have to name it like an alkane first, and then replace this E with OL. That would be your parent chain. And if there are any substituents, you tell where exactly are the substituents located. So the rules are same. You first find your longest chain, okay, and in this case, when you're numbering your carbon, we will give preference to the hydroxyl group. Okay, so now let's start numbering our carbon. Which one is our longest chain? My brain is telling me right now that this is my longest chain. So I'm gonna assume this and start numbering for now. Okay, so hydroxyl gets the preference, so I will start numbering from the right side. So if this is carbon number 1, 2, 3, 4, 5, 6. Right? So this is 6 carbons. What else can I number it? I could do this, that this is 1, this is 2, this is 3, this is 4, this is 5. Instead of going straight, I could go up. This is 6. So that is also giving me 6 carbons. So if you choose this green line, that is also perfectly okay. As long as both of them have 6 carbons, it's straight chain, so it really doesn't matter. Okay, but I'm gonna stick to the previous one and we'll name the compound based off of that. So now what do we do? This is my parent chain. So what is the name of the parent chain here? This is 6 carbons, so it will be hex. If it was alkane, I would call it hexane, but so this was our alkane, the parent chain is hexane, but in this case, what is this parent chain? It also has a hydroxy group, which means this is not an alkane, this is actually an example of alcohol. So we would replace the E at the end and replace it with OL. So what would be the name now? The parent chain would be called hexanol. And where is the alcohol located? Is it on carbon 1? No, it is on carbon 2. So we do have to mention that this is 2-hexanol. So that is name of my parent chain. Now I name the substituents. How many substituents does this have? Only 1, which is called 1 carbon. So this is methyl. Where is it located? Carbon number 5. So this is 5-methyl. So now it would be 5-methyl-2-hexanol. Okay, so naming is same approach. You basically start with finding the longest chain, then you name your alcohol with the OL at the end, replacing the E from the alkane name with OL. And if the hydroxy is on carbon number 1, you don't have to mention it, but if the hydroxy is located on any other carbon, you have to tell where is the hydroxyl group located. And then you name your substituents like you have been doing from before. Okay, let's try some more examples. Okay, this A we already named it, this is the same compound. Let's name the next one. So what do you see here? Actually, the A is not the same compound. Let's name A. My bad. A is not the same compound. First thing we have to do is find our long chain. Find our long chain, which is this I see right here. Which side should I start naming it? From the right side, because my hydroxy needs to have the lowest number possible. So this would be 1, 2, 3, 4. I could go up, make it 5. I could go right, straight and make it 5. It doesn't matter. Okay. This time let's say I go up. Okay. So what is my longest chain? My longest chain is 5 carbons, which means it is pentane. But instead of E, this is going to be all, because it has a hydroxy group. And where is the OH located? Carbon 2. So this is 2-pentanol. And now we name the substituent. If this is my long chain, this is my substituent, which is again methyl. Where is it located? Carbon number 4. So this is 4-methyl. So it would be 4-methyl-2-pentanol. Next we come to part B. What do we see in part B? You see a ring structure. And with the ring structure, you see alternating double bond and single bonds, which means this is benzene ring. Okay. And what do we know? What is the name of the benzene ring with an alcohol? Benzene ring with an alcohol group, hydroxy group. Phenol. Right, so this name we already know. Benzene ring with an OH group is called phenol. And where do we start the numbering? The numbering will start right here. This would be our carbon number 1. And now I go and number the rest carbon. I could go clockwise, which is this direction, or I could go this direction. Sorry, clockwise, which is this direction, and I could go counterclockwise. Which direction should I choose? Counterclockwise, because that would give my substituent the smaller number. So this is wrong. I would go 1, 2, 3. So where is the bromo located? It's on 3rd carbon. So this would be 3-bromophenol. There's no dash. There's no number. So no dash. 3-bromophenol. Whenever you see a benzene with an alcohol group or a hydroxy group, that is phenol. And that take that as your parent chain. Alright, just showing you the rules in words, what we just did. Okay, so those are alcohols. That's how you name alcohols. You could try a bunch of examples. We'll do some more examples at the end of this chapter, but that is how you simply name alcohols. Okay, next we come to the next compound or the next functional group, which is thiol. They consist of sulfur. The group is called SH group. Okay. Thiols have, how do you recognize thiols? They have a very bad odor. A very strong and very bad odor. Very pungent odor. For instance, cheese, onions, all the odor via garlic. What is the smell that garlic has? That is because of the presence of thiols in it. Okay, so cheese, onions, garlic, all those smells are because of thiols. Skunk. We know that the spray of skunk, it has a very weird smell, very bad smell. That is also because of the presence of thiol in it. Okay. Also, methane. We know our gas, the natural gas that we get in our stoves, that is methane gas. It is an odorless gas, which means it has no smell to it. But when we leave the kitchen stove gas open, we smell something, right? What is that smell? That smell is because methane is mixed with a little bit of thiol in there, so that whenever there is a gas leak in our house, we can actually smell it, and we know that we have to go and check on the gas stove. Okay, so to prevent any kind of gas leaks and to help detect it easily, we usually add some amount of thiols into those gases, into methane gas. Okay. All right. So now, how do you name thiols? We'll name the thiols the same way like we have been naming the other compounds. Okay. And in this time, thiol will be given the preference. So thiol should get the smallest number possible. Okay. For instance, you can see this is the compound that is present in the skunk spray, because of which it smells so bad. So it consists of trans 2-butene 1-thiol. Okay. So if you were to name it, let's say name was not given, how would you do this? You see the compound, you find the longest chain again. What is the longest chain? Right here, thiol. So it will be given the preference. So this is 1, 2, 3, 4. We see it has a double bond, so this will be 4 carbon with a double bond, so it would be called butene. Where is the double bond located? Carbon number 2, and it has a thiol on carbon number 1, so this would be butene 1-thiol. You don't have to tell it's trans or cis unless the question is asking, right? But most of the times I will give you a compound with thiol without a double bond or a triple bond. Okay. Let's see, how do we name these? Again, the IUPAC system tells us to give the preference to thiol. So how do you name them? You simply write the name of the alkane followed by thiol. That is how you usually write these compounds. You do not replace any alphabets, you do not miss out on any alphabets. It's simply alkane followed by thiol. If the thiol is on carbon number 1, you don't tell the number, but if it is present on any other carbons, you simply give the number or the location of thiol as well. For instance, what is this compound? How would we name this? This compound, first thing you recognize that it has a thiol in it. It has a functional group of SH, which means this is thiol. And how do you name it? You name the alkane. What is this alkane? This is 1 carbon alkane, which is called methane, followed by thiol. Okay. Next we find this compound. What is this compound? First thing you recognize, okay, this is a functional group of thiol. How do I name thiol? Thiols are alkane thiols. Only thing you have to remember is the rule. How do you name it? Okay. And then everything is named like an alkane. So now, what is the name of this alkane? It is 2 carbon alkane. So this is ethane, followed by thiol. It is carbon 1, so we don't have to give it a number. It is simply ethane thiol. Okay. Next we try to name this compound. Again, the functional group, first thing I recognize that this has a functional group of S8, which means this is thiol. So how do I start naming it? Name it like alkane followed by thiol. So where this is an alkane, how do I number it? I would give preference to thiol. So I could start numbering from the left, or I could start numbering from the right. But we would give preference to left, because thiol will get a smaller number that way. So if this is 1, 2, 3, 4, which means what is the number of thiol here? Carbon number 2. So this would be butane. Alkane is called butane thiol, and where is the thiol located? Carbon number 2. So this is 2-butane thiol. Thiols are very easy to name, very straightforward, right? Okay, so if we start naming these compounds, starting with A, what do we see here? Again, hydroxyl group, which means this is a alcohol hydrocarbon. So we start numbering, and in this case hydrocarbon, which carbon would be given preference? Our alcohol carbon would be given preference. So this is 1, 2, 3 and 4. You could be starting from the left side as well, but we wouldn't, because our hydroxy is given the preference. So in this case it's 4 carbons, so this would be butane, and its alcohol, so ending would be ol. So butanol. And what is my substituent? Our substituent here is 3-chloro. So this would be 3-chloro-butanol. If you would prefer, you could also write this as 3-chloro-1-butanol. That is also acceptable. Okay. Right. Moving on to number B. We need, again we see it's an alcohol, so we need to find our longest chain. There are various ways I can number this. I could start from, again I want to give my alcohol the preference, so I would try to start from the end which is closer to alcohol, which is right here. So I could go 1, 2, 3, 4, 5, 6, 7. There is no need for me to start from the right end or from any of these corners because they would not give alcohol my preference. So the best preference I could get for alcohol is starting from here. But now let's see, if I go up anywhere, would I get a longer chain? So if I go 1, 2, 3, 4, 5, that would be only 5 carbons, so that's not correct. I could also go 1, 2, 3, 4, 5, 6, 7. I could go up here. That would be also 7. So it's okay if I go up here or if I keep it right there, right? It doesn't make a difference. So now this is 7 carbons, meaning this is heptane, but it's an alcohol, so it would be heptanol. And my substituents, if this is my longest chain, should write it up here maybe, heptanol. If this is my longest chain, what are my substituents? Right here, and right here. Where is the alcohol located? 2, so this is going to be 2-heptanol. Now I put my substituents. I have a 6-methyl and a 4-methyl. So this would be 4,6 dimethyl. 4,6 dimethyl dash 2 dash heptanol. Okay. Next we go to C. Again, what do I find here? When I look at the molecule, I see alcohol. At the same time, I see a benzene ring. And we know whenever we have a benzene with OH, that group can be given one name by itself, which is called phenol. So my parent chain now is going to be this, which is phenol. And if there are any substituents, I would use that as a substituent and name it in front. The substituent I have is 1 carbon, which is right here. This is methyl. Where is it located? I need a number for it. So I have to put this as carbon number 1 always. Whichever final name I'm taking, I have to give preference to that particular group, functional group. So in this case it's phenol, so it's hydroxy group. So that would be 1, this would be 2. So name would be 2-methyl-phenol. Okay, let's try the last one. This is also, I see when I look at the structure, my parent chain, I would regard it again as phenol. And then I have substituents, which is right here. And how many carbon is my substituent? This is 1 carbon, 2 carbon. This carbon right here is not included because it is a part of the parent chain. So 2 carbon meaning it's alkyl, eth, so name would be ethyl. And what is the number? Where is it located? This is 1, 2, 3. So this would be 3-ethyl. So name would be 3-ethyl phenol without any spaces in between. 3-ethyl phenol. You can look for which is, I forgot to mention in the slide, this could also be called as ortho, the one that we just saw, 2-methylphenol, which was this was OH and this was methyl. So in this case, whenever it's 1 and 2, when you have 2 groups on 1 and 2, it is usually called as ortho, right? When it is present on 1 and 3, so for instance what we saw here, this was 1 and 3 had this, so this could also be called as meta, M. And when it is 1 and 4, when you have 2 groups, one is on 1, another one is on 4, it could be also called as para. So you should know these ortho, meta, para terminology as well. Okay, next we move on to the other type of functional group, which is ether. How could you recognize a compound has ether? And ether would always be R-OR. That means you have certain carbon and then it could have something else around here or not. O, another carbon, it could have something else, anything else on the other side. Basically the group we are looking for is COC bond. As long as there is a COC bond, it is an example of ether. This could have other alkyl group, aromatic groups, it doesn't matter. Okay. This usually has a bind structure just like water and alcohols, something like this. Okay, and it has the common name that gives the alkyl names of the attached group followed by ether. So usually in this case, instead of learning our IUPAC naming system, we are going to learn the common names. Okay, how do you name them with common name? You simply first you see that this is an ether, then you figure out what is the group that is present on one side of the ether, what is the group that is present on the other side of the oxygen. Okay, so what is this group on one side? This is methyl. What is the other group on the other side of oxygen? This is also methyl. So this will be called dimethyl ether. So you treat both the sides of the oxygen as different alkyl groups and you name them separately, followed by a word ether. Okay, so now for most of the ethers, we again, like I said, use common names. If you have two different alkyl groups, for instance in the previous one it was both methyl, if you have two different alkyl groups, how would you name it? You would follow the alphabetical order. Okay, for instance in this case, this is the first thing we have to recognize, that this is an ether. It has a COC bond. Then you find whatever is attached to the oxygens separately. So on one side of oxygen we have a methyl group, on the other side we have 3 carbons, which is a propyl group or a propyl group. So now how do we name it? We are going to name it by the alphabetical order. Based on that, methyl comes first, so it would be methyl propyl ether. Okay, so for ethers we are not going to worry about IUPAC names, we are only going to look for the common names. If you were to given the name and you were to draw this compound methyl propyl ether, how would you draw it? First thing you recognize is, again, like I've said before, whenever name is given to and you have to write the formula, always start from the far right. Okay, so first you should always look at the very end and recognize what is this compound. So this is an ether, which means it has an oxygen and it has alkyl groups on both the sides. What are the alkyl groups? It's telling you. One is methyl, so 1 carbon. The second is propyl, so 3 carbons. 1, 2, 3. And then you fill up the rest with hydrogens. So this carbon already has 2 bonds, which means it needs 2 more, so 2 hydrogen. This carbon also has 2 bonds, so it needs 2 more, 2 hydrogen. This carbon has 1 bond, it needs 3 more, so 3 hydrogens. Okay. Okay, let's see if we can go from naming to the formula. So write down the structures for the following compounds. So the first one is 3-pentanol. So again, start naming, always started from the far right corner. So this is telling me this is an ol, which means it's an alcohol. How many carbon? 5 carbon, pentane. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 carbons. It is telling me the first carbon has, the third carbon has the alcohol. So you could start numbering from wherever you want, since you are drawing the structure right now. So I would start from here, 1, 2, 3, 4, 5. It really doesn't matter where we begin. Okay, 3, and I would put 1 alcohol right here. So my final structure would look like this, and I would get rid of these numbers, because when you're giving the final answer, you of course don't give the numbers. So this would be 3-pentanol. Next we have is ethanol. So again, ol at the end meaning alcohol, so it has OH. How many carbons? Eth means 2 carbons, so 1 and 2. That's it. And you could draw alcohol on either side, it really doesn't matter. So you could draw alcohol right here, or you could write, if the question doesn't specify it wants condensed or line structure, so you could draw like this as well, whichever you feel comfortable with. 2 carbons, one of them has an alcohol which is OH, rest you fill everything else up with hydrogen. So this carbon already has 2 bonds, it needs 2 more. Total is 4 always, needs 2 more, so you would add 2 more hydrogens to this. This carbon has 1 bond, needs 3 more, so we will add 3 hydrogens. So you could draw this or this, really doesn't matter. Yeah, you could draw it in a corner and then draw this as alcohol. That would work as well. But what would be wrong if you draw this and you put an OH right here? This is telling me that there is only 1 corner here. So this would be, this is not ethanol, this is now methanol. So this is wrong. Okay, because this structure is methanol. Each carbon has to be given 1 corner. That is why I drew it like this and went down and put an alcohol. Or I drew it like this and then went the other way and put an alcohol, because each corner is regarded as 1 carbon. Okay. Right, next we have diethyl ether. So from the far right, it tells me it's an ether, meaning this is O with 2 alkyl groups. What are the alkyl groups? Diethyl, meaning 2 ether groups, 2 ethyl groups. Eth means 2 carbon, so on both the sides I have 2 carbon groups. Carbon, carbon. Fill up the rest of the bonds with hydrogen. This carbon has 2 bonds, needs 2 more hydrogens. This carbon has 1 bond, it needs 3 more bonds, so 3 more hydrogens. This carbon already has 2 bonds, it needs 2 more, so 2 more hydrogens. This carbon has 1 bond, so it needs 3 more, so 3 more hydrogens. Or if you want, you could draw it in the line structure format as well, which would be, this ether would have 1 and 2, 1 and 2. Both sides should at least have 2 corners. So either of these would be correct. Next, we'll talk about all of these properties. So we just finished the naming. Now we'll talk about their properties. Oh no. We will talk about their properties of all these compounds and certain reactions that they undergo. Okay. So the first thing is, we'll talk about classification of alcohols. So alcohols can be classified into 3 different categories, which is called primary alcohol, secondary alcohol, or tertiary alcohol. What does this mean? Basically, the carbon that has the alcohol group, if it is bonded to 1 more carbon, it would be primary alcohol. Primary means you write this as 1 degree. Okay, so 1 degree primary means this carbon which is bonded to the alcohol, if it has 1 more, if it is bonded to 1 more carbon, it would be primary. If the carbon which has alcohol is bonded to 2 more carbons, it would be secondary. If it is bonded to 3 more carbons, it would be tertiary. Okay, so for instance, in this structure, the carbon that is bonded to hydroxy is this. How many more carbons is this bonded to? Just 1. So this is primary alcohol. This carbon is the one which is bonded to alcohol. And how many more carbons is this bonded to? 2 more carbons, 2 more alkyl groups. So this is secondary. Then the carbon here is bonded to alcohol. And how many more carbon or alkyl groups does this have? 3 other alkyl groups. So this is tertiary alcohol. Okay. So for instance, classify each alcohol as primary, secondary, or tertiary. So which carbon are we looking specifically for? The carbon which has the hydroxy group. So in this case, this is the carbon that has hydroxy group. And how many more carbons is this bonded to? This is bonded to carbon here and carbon on the other side as well. It doesn't matter how long the chain is. This carbon is bonded to one carbon on this side, one carbon on that side, so 2 more carbons, which means this is secondary alcohol. Okay, so only thing you're looking for is how many more alkyl groups is this bonded to. Just look for these bonds that are next to this carbon. How about this? So in this structure, where do we see the hydroxy group? Right here. Which carbon is it bonded to? This. How many more carbons is this carbon bonded to? 1. How many bonds does this carbon have with another carbon? There is only one bond with one more carbon. Okay, we are not looking for what is the long chain, we are not looking for what is the chain, we are just looking for how many carbon this carbon has to have one bond with the carbon. Okay, the next atom next to this carbon should be a carbon. So if you were to expand this structure, how would this look like? This would be this carbon with a hydroxy, 1 hydrogen, 2 hydrogen, and then we have a CH2 right here, and then we have a CH3 right here. So this carbon is bonded to 2 hydrogen, 1 hydroxy, and 1 alkyl group. This alkyl group is eth. It doesn't matter. But how many? There is only this carbon has one bond with another carbon. That carbon is bonded to another carbon. It doesn't matter. We don't care about this carbon. We are only looking for the carbon which has the hydroxy group. Okay, so this carbon right here has one bond with another carbon. Another way to say this, if this is confusing, is how many carbon-carbon bonds does this carbon have? Okay, so carbon-carbon bonds, the carbon which has the hydroxy, how many more carbon-carbon bond does this have? Okay, so for instance, let's redo this first one. So for instance, this is the carbon, right, in the middle. How many carbon-carbon bond does this carbon have? This carbon has one carbon-carbon bond right here on this side, one carbon-carbon bond on the other side. So it has 2 carbon-carbon bonds, which means this is secondary. It doesn't matter how long the chain is. It is directly bonded to one carbon, and then the other carbon is bonded to whatever, it doesn't matter. Okay, for instance, again in this case, what is this? This is CH2. This is the carbon that is bonded to hydroxy. So how many more carbon-carbon bond does this have? This has one more carbon-carbon bond. So this is primary. Let's try the third one. So which carbon is the one which has hydroxy? This carbon right here. How many carbon-carbon bond does this have? This has one carbon-carbon bond right here, second carbon-carbon bond right here, third carbon-carbon bond right here. So it has 3 carbon-carbon bonds, therefore this is tertiary alcohol. Okay, we don't care what is following after this. We don't care about that. What we care is this particular carbon, how many carbon is it directly bonded to? How many alkyl group is it directly bonded to? So this can be regarded as one alkyl group. This is one alkyl group. This is one alkyl group. So this carbon is bonded to 3 different alkyl groups. Therefore, this is a tertiary alcohol. Why is this important? Primary, secondary, tertiary? Because this affects the properties of alcohols. For instance, this affects the solubility of alcohols. Okay, what do alcohols consist of? They contain a polar bond, which is the hydroxy bond, OH group, right? And OH group, what can OH group do? OH group can form hydrogen bonds with water. Remember, hydrogen bond is whenever hydrogen is bonded to any oxygen, fluorine, or nitrogen, it can form hydrogen bonds. So in this case, we have hydroxy group, which is OH. So this hydrogen is bonded to oxygen, and then we have any R group. It doesn't matter how many R groups there are, right? So this oxygen would be partially negative. This hydrogen would be partially positive. And what is present in water? In case of water, what do we have? it is HOH. This oxygen, this water, oxygen is partial negative, hydrogen is partial positive, hydrogen is partial positive. So this hydrogen from alcohol can form a hydrogen bond with the oxygen in water. And that is why this group essentially can be, this increases the solubility of alcohols in water. The more hydrogen bonds it can form, the more soluble it will be with water. More interactions it can have with water. So for instance, one you could see is so this is showing you all the types of hydrogen bonds that it can form. For instance, this is water. Red ball right here is oxygen, so it is partial negative, and then there are these white, which is hydrogen. So, and what is this? This is showing you the alcohol. So this is our alkyl group. This is CH3 methanol, so CH3OH, and this is the oxygen, this is the hydrogen. This hydrogen right here, let me write it, this is O, this is H, this is O, this is H from water. Okay, so this oxygen is partial negative. Oxygen can form hydrogen bonds with water molecules, the hydrogen from water molecules, right? And what happens to this hydrogen? This hydrogen from hydroxy can form a hydrogen bond with the oxygen from water molecules. So for instance, right here, this oxygen can also form a hydrogen bond with another water molecule. So one alcohol can be involved in multiple hydrogen bonds. For instance, you can see this OH group can be involved in 3 hydrogen bonds with water, which makes it soluble in water because it can interact with water. This is also polar, methanol is also polar, and water is also polar. So they interact with each other, and they are soluble because they interact and form hydrogen bonds. Okay, but what is the problem? When the number of carbon atoms that are attached to this OH group, only polar group here is this OH, right? The number of these carbon chains is, this carbon is not polar. None of this part is polar. So if we increase more and more carbon chains behind this, it will decrease the solubility of that alcohol. Okay, what does that mean? So the alcohols that have 1 to 3 carbons are soluble in water. The solubility of alcohols in water decreases with the increasing number of carbon, because this is soluble, so this has 2 carbons, 2 carbon chain and 1 OH group, so this is soluble in water. But what about this? Now this has too many carbons attached to this, and the whole chain here is non-polar. So this increases the or decreases the polarity of the molecule. Okay, so having more number of carbon basically decreases the polar effect of this hydroxy group now. This is a very tiny group which is polar. If I add a very long chain of non-polar compound right next to it, it will decrease the effect of this, right? So therefore the solubility decreases. So usually alcohols which are from 1 to 3 are soluble. Anything more than that is not soluble in water. So for instance, if you see methanol would be, it has only 1 carbon, so it would be soluble in water. Ethanol only has 2 carbons, so this would be soluble in water. Propanol only has 3 carbons, so it would be soluble in water. Butanol has 4 carbons, so it is still trying its best to be soluble in water, but it is only slightly soluble in water. But anything above this, as I increase the carbon numbers, pentanol, hexanol, heptanol, decanol, octanol, doesn't matter, it's all going to be insoluble because that small hydroxy group cannot keep it soluble in water. Same is true for ethers. Okay, so you can see right here, this is solubility of alcohols and ethers. Same is true for ethers as well. What do ethers have? Ether also have this group which is ROR. This oxygen, ROR. R is basically carbon chains, right? So this oxygen also has lone pairs. So this is also, if it wants, it can share this lone pair with water to form a hydrogen bond. So now if you put ether in water, what would happen? Water has again oxygen and it has these hydrogen, which is partial positive, partial negative. So this hydrogen which is positive can form hydrogen bond with oxygen from ether. Same thing here, you could have another water molecule that can form, this is partial positive and oxygen partial negative. So this oxygen can form hydrogen bond with, this hydrogen can form a hydrogen bond with oxygen from ether. So this would also make ether soluble in water, but whenever this group increases, the size of this group would increase, it would become less soluble, right? Okay, how about phenols? Phenols are also alcohols, right? Only difference is these are aromatic alcohols. So they also have this OH group that can also form hydrogen bond with water. They will also dissolve in water, but not a lot. They are slightly soluble in water. What do they do in water? They can get rid of this hydrogen. They can donate this hydrogen to water and turn into O- and H3O+. Where have we seen such reaction before? When acids. Perfect. When something donates hydrogen, that means it's an acid. So what is happening here? This phenol is donating. It lost its hydrogen. So this becomes acid. This is proton donor. And this water accepted the hydrogen, so this became base. This is proton acceptor. So this is telling you that phenols can essentially act as acids in water. Phenols are acid, but again, what kind? They are very weak acids because they do not dissolve completely. They do not dissociate completely. They are only slightly soluble, so they only slightly dissociate. Okay, and what is this ion called? This is called phenoxide ion. Phenoxide ion coming from phenol. And what is this? This you already know is hydronium ion. So phenols in water can behave like acids, but they are again very weak acids. Okay, so let's try this question. Indicate whether each of the following is soluble in water and explain why. So is A going to be soluble in water? No. Why? Because the number of carbons attached to this small polar group is 1, 2, 3, 4, 5, 6 carbon chain. So anything less than 3 is soluble. Equal to 3 or less than 3 is soluble, but anything more than that is, butanol is slightly, but anything more than that is completely insoluble. So this is no. How about the second one? This only has 2 carbons attached to the polar OH group. So yes, this is going to be soluble in water. Okay, so explanation: alcohol with long carbon chains are non-polar. Short chain alcohols can form hydrogen bond with water, therefore they are soluble in water. Okay, so the next we would look at certain reactions that these compounds undergo: alcohols, ethers, and thiols. So the first reaction we'll look at is dehydration of alcohols. Dehydration means, just like the name tells you, dehydration is removal of hydration. What is hydration? Water. So alcohols can undergo dehydration when they are heated with an acid catalyst. So whenever you see an acid involved, acid catalyst like H+, HCl, H2SO4, and there is some heat involved, it is going to dehydrate the alcohol. How? The hydrogen and OH from adjacent carbon atoms will be lost. What does that mean? For instance, if this is the alcohol that is given to you, what is this? This is CH3 bonded to CH2OH. Okay, so this is simply a molecule of ethanol. Oops. This is ethanol. You could also write this as what you see here, CH3 CH2OH. This is what's written. So what would happen here? We are heating it in presence of acid. That means this is an example of dehydration. Water will be lost. Water is HOH, that is H2O. So we need to get rid of OH from one of the carbons, and the second adjacent carbon next to it is going to lose the hydrogen. So where is the OH coming from? This, the adjacent carbon, there's only one adjacent carbon, so this is going to lose its hydrogen. This water will be lost as H2O. What would happen? Now this carbon would have one empty bond, this carbon would have one empty bond, so they are going to make a bond with each other and convert it into alkene, make it into a double bond. Okay, so what is dehydration? Whenever alcohols undergo dehydration, they form alkenes. So ethanol will be converted into ethene. Okay, always alcohols undergo dehydration to form alkene. Water is lost, one of the carbon loses, the adjacent carbon is going to lose hydrogen, and the carbon which has hydroxy is going to lose its OH group. Okay, in this case it's easy because there's only one adjacent hydrogen. What if I have another molecule? So what if we have a molecule that is like this? So let's say 1, 2, 3, 4. Okay, so this has OH, this has CH3, this would be CH2, this would be CH3. What if this is our molecule? And I ask you, what would be the dehydration product for this? So we have heat and H+. I ask you simply, what would be the product for this reaction? You should recognize that this is a reaction of dehydration. Dehydration means it's going to lose water. Where is the water coming from? OH is coming from this. Hydrogen has to come from the adjacent carbon. Which carbon now? Should you choose this hydrogen coming from this carbon on the left, or should you choose this carbon on the right? This is based on, again, Markovnikov's rule. What did we say there? We said rich gets richer and poor gets poorer. Okay, so in this case we are going to use the rule of poor gets poorer. Okay, so whichever one, what does this mean? This rule tells you whichever carbon, adjacent carbon, that has less number of hydrogen is going to lose or will lose hydrogen. Okay, so out of these two sides, which carbon has less hydrogen? This carbon has 3 hydrogen atoms, this carbon has 2 hydrogen atoms. Which one is poorer in this case? This is poorer, this is the poor one, so this is going to get even more poor by losing 1 more hydrogen. Okay, so we are going to take hydrogen from this carbon, so this would stay as it is. This is going to turn into, OH will be lost. From this carbon, 1 hydrogen will be lost, so it would have 1 extra bond as well. What would they decide? They'll decide to share this bond with each other, and water will be lost. So we saw this rule, basically rich gets richer when we were adding. So this was the reaction where we were hydration of alkene. We saw this reaction in previous chapter where we did hydration of alkene. Hydration of alkene is basically opposite reaction. You see, this is alkene. If you add water to it, it is hydration, and we saw what was the rule? Rich gets richer. Right? So in that case, if I were to add hydroxy, who would get the, one of these would get the hydroxy, one of these would get the hydrogen. So that's where we were using this rule, rich gets richer. But when do we use this poor gets poorer? That rule is used when we do dehydration of alcohol. So dehydration is simply this reaction going in forward direction. So the carbon, this carbon is going to lose the hydroxy, the adjacent carbon is going to lose the hydrogen. Now this carbon has 2 adjacent carbons, this also has hydrogen, this also has hydrogen. The question is, which carbon is going to lose the hydrogen out of these? Which one? Whichever one has the lesser amount of hydrogen is going to lose its hydrogen. So poor, this is already poor in comparison to this one because it has less hydrogen, so it would get poorer. Right? So that is Markovnikov's rule. It basically helps you in adding a adding a water or removing a water. Remember this rule whenever you are doing either a hydration reaction of alkene or dehydration of alcohol. Right? Okay, next we'll talk about two other reactions, which is oxidation and reduction. So what is oxidation? We have seen before, oxidation we saw was Leo. Leo means, or we saw oil rig, right? For you guys we did oil rig. So what was oxidation? Oxidation is loss of electrons, right? We saw this before. Oxidation was loss of electrons, and we saw what was reduction. Reduction is gain of electrons. But this is very helpful when you're working with inorganic compounds. In organic chemistry, we use a little different definition. It's the same thing. It's based on the same principle. But in case of oxidation, we increase the number of carbon-oxygen bonds by either adding an oxygen or by losing hydrogen atoms. Okay, so you could redefine oxidation here as oxidation is basically either you add oxidation, either you add oxygen or you increase the bond with oxygen, increase carbon bond with oxygen, or you remove hydrogen. Adding oxygen or removing hydrogen. And reduction would be what? Reduction would be opposite of that. Okay, reduction would be opposite, meaning you remove oxygen, you decrease the carbon-hydrogen bond, or you would add a hydrogen. That would be reduction. Okay, that is how you could understand oxidation and reduction specifically in organic chemistry. What does that mean? How would you? For instance, like this. If I tell you this is the alcohol and I ask you what would be the oxidation product of alcohols. Oxidation of alcohol means you are going to increase the carbon-oxygen bond, or you add another oxygen, or you remove hydrogen. So alcohols undergo oxidation to produce another functional group which is called aldehyde. Okay. This is another functional group which is C double bond OH. This group is called as aldehyde. What is happening here? Currently you see this is CH3, CH2OH, or let me draw this bond right here so it's more visible, OH, right? Now the product here is C double bond OH. So what is happening here in case of oxidation? You can see the number of bond between carbon and oxygen in alcohol was 1, but in case of aldehyde it is double bond between carbon and oxygen. So we have essentially increased the number of bond with carbon and oxygen. So this is an example of oxidation, and we also lost one of the hydrogens from this carbon. So basically you can see what is lost is this hydrogen, and this hydrogen is lost, and there is a double bond between carbon and oxygen. Okay, so what you need to remember here is alcohols, when they oxidized, they would produce aldehyde. Which type of alcohols? Primary alcohol. That is when your primary, secondary and tertiary would become very crucial. Okay, the primary alcohols are oxidized to produce an aldehyde group. One hydrogen from here and one hydrogen from this carbon, the same carbon, are going to be lost, and it would form a double bonded oxygen. So this had 3 hydrogens. This, one of these hydrogens and one of these hydrogens are lost, and this carbon and oxygen are going to form a double bond with each other. That is oxidation. And who would do this? This can be only done by primary alcohols. When primary alcohols do this, they are going to produce aldehyde. How about secondary alcohol? There's one more step sometimes. When you have aldehyde formed, this is another group that I'm going to add to your list right now. So what happened? The primary alcohol got oxidized and it produced aldehyde, which was CHO, right? This can further be oxidized. How? It would form another, you could add another oxygen into this and it would form a group which is called carboxylic acid. So this is CH3COOH. This is RCOOH. This group is called carboxylic acid. So these are basically organic acids. That is how organic acids look like. If you ever see anything with RCOOH, this means this is a carboxylic acid. So now you know alcohols, ethers, thiols, and now you know aldehyde, ketone, and carboxylic acid. Okay, so what is happening here? Essentially the primary alcohol, which was, let's say R, I would put another carbon here, CH2OH. Primary alcohol will oxidize. Oxidize is usually written like this. Okay, will oxidize to form aldehyde, which is R. This hydrogen and this one of these hydrogens will be lost and it would form C double bond OH. This is aldehyde. This can further be oxidized to produce RC double bond OH. So you simply add one oxygen here and this is called carboxylic acid. And this was the primary alcohol. Okay, so primary alcohol will first oxidize into aldehyde, which will further oxidize into carboxylic acid. Whereas secondary alcohols, they essentially form ketones. If we have secondary alcohol, what would the secondary alcohol do? In this case, you can see this is the alcohol. When oxidation, what does it do? It loses this hydrogen from OH and it loses one more adjacent hydrogen from the same carbon. Right? This would be lost and this carbon and oxygen will form a double bond. Now this group that you see is called a ketone. This is another functional group which is called ketone. What is happening here? What do we have here? This is R, C, double bond O, R. This group is called as ketone. Okay. Previously we saw, a lot of times students confuse this with ether. Previously we saw ether, which was ROR. These two are different. How? This was ROR, this is RC double bond OR. So this is RCOR. Okay, this is called ketone. So essentially whenever secondary alcohol is oxidized, it is going to form ketone. Why? Because this only has, secondary means it has two carbons attached to it. So it will always produce this particular group, which is ketone. What happens for when we are working with tertiary alcohols though? In case of tertiary alcohols, how would tertiary alcohols look like? They would look something like this. This is the carbon. It is already bonded to three other carbons, three other alkyl groups and an OH. So what we saw when an alcohol is oxidized, one hydroxy group is lost and hydrogen from the same carbon is lost. But in case of tertiary alcohols, they don't have any hydrogen left. They don't have any hydrogens here, this carbon. So which means these tertiary alcohols cannot be oxidized. They do not readily oxidize because there is no hydrogen atom on the carbon bonded to the hydroxyl group. Okay, so since there is no more hydrogen here, it cannot lose a hydrogen from here and hydrogen from here. It doesn't have any hydrogens left. So tertiary alcohols do not oxidize because they do not have a hydrogen. So out of primary, secondary and tertiary alcohol is the one that does not oxidize. Primary alcohols will produce aldehyde and carboxylic acid. Secondary alcohols will produce ketone, and tertiary alcohols do not oxidize. The questions would simply look like I could give you one of these alcohols, and I could ask you what would be the oxidation product for this alcohol, and we'll look through some of the questions later on. Okay, last is oxidation of thiols. Thiols can also undergo oxidation. Okay, remember one of the definition for oxidation was removal of hydrogen, right? So in this case you are going to see, in case of thiols, hydrogens are removed. So what is the thiol group? Thiol was RSH. What would happen here? Two molecules of RSH will come together and these hydrogens will be lost. When these hydrogens are lost, this sulfur will have one extra empty hand, this sulfur will have one extra empty hand, and they are basically going to join hands together and form RSSR. This is now a disulfide. It has two sulfurs, so this is called disulfide. Okay, so essentially what is happening, this hydrogen, I'm not going to erase this hydrogen and this hydrogen will be lost, so it would have this extra hand which they are going to join with each other and they'll form a disulfide molecule. So now this R can be anything, it doesn't matter. As long as there is an SH group, they will oxidize to form a disulfide bond. Okay, where do you see this example? When people curl their hairs, that is an example of cross-linking of disulfide bonds. So what essentially happens is our hair has bunch of, this is one of the proteins, cysteine, okay, which is found in keratin. Keratin is the protein that makes up our hair. So basically this amino acid has this particular SH group. This is an example of a thiol group. So this amino acid is an example of thiol group. So it has SH. What happens? You basically heat the hair and then you curl it, you put it in a certain direction, and then as one thiol group and the other thiol group come closer to each other, they can form this disulfide bond and it holds the hair in that particular position. But eventually what happens, these disulfide bonds again get reduced slowly over time, so your hair comes back to its original state. Okay, so for instance, some people have curly hair to begin with or a frizzy hair to begin with. That is basically what's kind of is affecting that. Okay, so if there are a bunch of cysteines and these thiols are already oxidized, that means you already probably have a little bit of curl in the hair. So this is, it's not exactly just this, of course there are other factors, but this is like one of the factors that affects it. Okay, so disulfides are formed whenever thiols are oxidized. The question would look like, again, give you one particular example. For instance, I could simply give you this CH3, CH2, SH, and I could ask you what would be the oxidation product for this reaction. What would be your answer? You simply are going to join two of these molecules and it would form a disulfide bond. So it would be CH3, CH2. This thiol is going to lose this hydrogen and it will have this empty hand. And similarly, the other molecule, second molecule, which is CH3, CH2, SH, is going to lose its own hydrogen and it will have one empty hand and you simply join them together. So this is the final product. Okay.